You know how it is you want to wrap your head around the big stuff, the really fascinating ideas, without feeling like you're just drowning in jargon.
Yeah, totally.
We get it. So get ready for a bit of a perspective shift today. We're going to question something really fundamental: time itself.
Right.
Forget that idea of one single clock ticking away for the entire universe. Today, we're diving into time zones of the universe. It's this compelling idea that maybe everything, from the tiniest atom to the biggest galaxy, might actually exist in its own unique rhythmic bubble.
And what's really kind of mind-bending about this is how much it departs from the standard view.
Right.
We're just so used to thinking of time as this universal stage,
Yeah.
where everything happens.
Yeah, the backdrop.
Exactly. But the concepts we're digging into today, which are based on something called motion theory, they suggest something.
Yeah.
Well, something far more intrinsic. Time as an inherent characteristic of local systems.
Okay, let's unpack that. What is time, then, according to motion theory? Because the sources are pretty clear. It's not a force, right? Not something we push against.
No, not a force.
We're in a dimension we travel through, like space.
Right.
And definitely not this one-size-fits-all constant. So what's the picture it paints instead?
Well, at its heart, the core concept is actually surprisingly elegant. It's time equals local rhythm resolution.
Local rhythm resolution.
Well, think of it like the synchronization speed of any given system. It's determined by the structured motion happening inside it. Imagine like a really complex clock, lots of gears turning at different speeds, but they're all coordinated. The local rhythm resolution is like the overall speed and coordination of that whole clockwork mechanism.
So it's like everything has its own internal tempo, its own beat.
Precisely.
And the quicker its internal beats or ticks, the faster its time unfolds compared to something with a slower rhythm.
Exactly that. And this gives us a completely fresh way to think about something as basic as, well, getting older.
Aging, yeah.
Our aging isn't really dictated by some universal cosmic clock ticking away.
Right.
Instead, it's tied to how well our atoms, our cells, can maintain their internal motions, their own specific ticks.
So it's an internal process.
It's an ongoing process of internal synchronization, yeah.
Yeah.
Not a race against some clock out there.
Okay, this leads us to the really fascinating bit. The sources then take this idea and apply it to the biggest things we know, galaxies.
The cosmic scale.
Now, mainstream science talks about redshift as evidence that galaxies are moving away from us, right? The expanding universe idea.
That's the standard cosmological interpretation, yes.
Yeah.
Redshift as a Doppler effect, indicating outward movement.
But motion theory offers a completely different interpretation, doesn't it?
It does. Motion theory suggests that this redshift isn't primarily about motion through space. It's more likely a result of a mismatch in the fundamental rhythmic resolution rates between, say, our galaxy's synchronization pattern and the pattern of that distant galaxy we're looking at.
A mismatch in rhythm. So when we look at a really redshifted faraway galaxy, we're not just seeing old light that's traveled for billions of years.
Well, the light has traveled, but the interpretation of why it's redshifted changes.
Okay.
Motion theory suggests we're essentially observing its structure, resolving it more or less in real time.
Right now.
But its internal processes, its fundamental tempo, is happening at a slower rate compared to ours.
So it appears older or more redshifted because its clock is ticking slower relative to us.
Exactly. So when you gaze at those ancient-looking lights, you're not just seeing the past in the conventional sense. You're witnessing a reality that's unfolding at a fundamentally different tempo. Wow. The distance itself isn't the main factor causing the redshift in this view. It's more about the difference in the local time rhythm. We are resolving their structure live, you could say, but their internal ticks, their basic processes, they're just happening at a different rate compared to our own here.
Okay, that's definitely a mind-bending thought on the cosmic scale. But you mentioned this idea of local rhythm resolution also plays out much closer to home, like inside living things.
Absolutely. It's not just galaxies. Think about biology. Why can bacteria multiply so incredibly fast?
Yeah, ridiculously fast.
Compared to, say, the rate our own cells divide. Motion theory would suggest this is because bacteria operate within a much faster synchronization bubble.
A faster time zone, basically.
Essentially, yes. And our own bodies, in fact, can be seen as these nested hierarchies of time zones.
Nested hierarchies, like those Russian nesting dolls, one inside the other.
Precisely like that. That's a great analogy. You get DNA repair happening at one speed, right? Then cell growth may be a bit slower, tissue repair slower still, and ultimately, organ degradation over a lifetime.
All different tempos.
All occurring at different rhythmic resolutions, nested within each other. And all of these processes in us are considerably slower than the super-fast reproduction cycle of a bacterium. So this perspective really shifts our focus away from thinking about external timekeepers. The real drivers of our internal clocks are the inherent motion loops within our own biology.
Okay, so if we're already living in these nested time zones, this leads to a fascinating way to rethink something like time travel, right? Which is usually sci-fi stuff.
Exactly.
According to motion theory, it's definitely not about jumping in a DeLorean and zipping through a fourth dimension.
No, not quite like that. The theory proposes we are already living within a multitude of these time zones constantly.
Oh, okay.
So time travel in this context becomes less about traversing some external timeline and more about navigating the differences in synchronization between these existing zones.
The sources give some really cool examples here, like astronauts on the ISS aging just a tiny bit slower.
Right. That's a known relativistic effect, but motion theory offers a complementary view.
And deep-sea creatures may be aging slower, too.
And even speculation about potential microbes on Mars having radically different internal rhythms.
So these aren't just explained by standard relativity, like time dilation due to gravity or speed from this viewpoint.
Motion theory interprets these phenomena maybe more fundamentally, not just as space-time bending, but as timing mismatches.
Mismatches?
Yeah, mismatches arising from differences in, say, gravitational synchronization convergence like near Earth for the astronauts, or different environmental synchronization pressures like the deep ocean.
Okay.
The fundamental rhythm of these systems gets offset relative to ours because their local motion loop environment is just different.
This really opens up some potentially huge implications, especially when the discussion turns towards intelligence.
Yes, that's a big one.
The idea that maybe galaxies out there with faster rhythmic resolution rates, they could potentially host civilizations that think, evolve, build just much, much faster than we can even imagine.
It's both exhilarating and, as the source notes, a little unsettling to think about.
So if a galaxy has a significantly faster internal tick, could their moments, their experience of time, feel like entire eons to us?
That's the implication. How would that fundamentally change their experience of history or communication or development? It's staggering.
It really raises a crucial question then, doesn't it? Could there be a fundamental link between the speed a system processes information, its rhythm rate, and its actual capacity for intelligence?
That's the provocative thought. If so, then the vast differences in these time zones across the universe could imply very different thresholds for cognitive complexity. Some zones might simply operate too slowly or perhaps too quickly in a chaotic way for certain types of intelligence to emerge.
Wow. Okay, now, for those of us maybe not deep into theoretical physics, the idea of motion math might sound a bit scary.
Understandable.
But the source gives a simplified formula. Head-ups. Okay. Can you give us the gist? What's this telling us?
Yeah, let's break it down. Essentially, this math is saying that the difference in how we perceive time in another system compared to our own time, it basically boils down to the ratio of their internal tick rates compared to ours.
So comparing rhythms.
Exactly. Zephyrafrec is the local rhythm resolution rate of the system you're looking at.
Got it.
And ARF is just a reference point for us. That's typically our Earth-based rate, our local resolution baseline.
Right.
The key point is our experience of time is inherently relative. It's tied completely to our own internal sync loop, our own local rhythm.
So there's no absolute time ruler.
Not in this framework. The observable universe from this perspective isn't just this vast spatial thing. It's also this incredible mosaic of different R values, different rhythm rates, each region kind of operating at its own temporal frequency.
This whole framework seems like it could open up some potentially revolutionary doors in, say, medicine. The concept of time-based medicine sounds fascinating.
Oh, definitely. The potential here is really exciting. Imagine understanding and treating diseases by focusing specifically on the synchronization rates of the biological systems involved.
How would that work?
Well, for example, if cancer cells operate on a faster, perhaps less stable rhythmic loop compared to healthy cells,
which they often do metabolically,
right, then the therapeutic goal could be to specifically disrupt that faster rate, maybe bring it back into sync or decohere it without affecting healthy tissue as much.
Targeted disruption.
Or consider aging. If aging involves a gradual degradation of this biological synchronization, a loss of coherence at the fundamental motion level,
Yeah.
then interventions might focus on restoring that coherence, maybe at the cellular or even subcellular level.
Wow.
Even understanding why some drugs work better on certain cells could be viewed through this lens of matching or mismatching internal time zones or sync rates.
That's a completely different angle. Now, the source used that great analogy of the universe as a cosmic time zone layer cake, or those Russian dolls.
Yeah, I like the Russian dolls one.
Can you expand on that a bit, this hierarchical view of motion systems?
Sure. Imagine starting at the bottom with the incredibly fast, almost jittery rhythms of fundamental particles like quarks.
Okay, super fast.
Then they combine, they structure themselves into protons and neutrons, which have slower, more stable rhythms.
Right.
Those form atoms with their own nested orbital synchronizations. Then atoms combine into molecules, which have their own complex vibrational and rotational loops, introducing inherent friction and delay.
Getting slower and more complex.
Exactly. And it continues up the scale. Molecules form cells, cells form organs, organs make organisms, then planets, star systems, galaxies, all the way up to the massive convergence zones of galaxy superclusters.
Each layer building on the one below.
Right. And each step up in this hierarchy introduces more complexity, more interactions, more parts that need to synchronize. And that naturally adds delay, adds friction to the overall sync loop of that larger system. So the key takeaway is that, generally speaking, more complexity tends to lead to a slower overall rhythm for the system as a whole.
That makes sense.
And it reinforces that idea that comparing, say, 1 second on the scale of a quark interaction versus 1 second on the scale of galactic rotation is basically meaningless without specifying which motion loop, which R value you're talking about.
So familiar concepts then, like time dilation from relativity or even gravity, they take on a whole new meaning in motion theory. It's not about space-time bending in the usual sense.
It's a reinterpretation, yeah. What Einstein mathematically described as time dilation, whether due to relative velocity or gravity, motion theory interprets that as an offset in rhythm density.
Rhythm density.
Yeah. Think about it. When you get near a massive object like a black hole, your internal motion doesn't just slow down because space-time is curved.
Yeah.
In this view, it's because that immense gravity represents a region of very high density of converging, structured motion. It makes it harder energetically for your internal rhythms to resolve and maintain sync with frameworks far away from that density.
It's like running through treacle.
Sort of, yeah. Or at very high speeds, your structure resists synchronizing easily with the patterns of slower distant zones, causing your local rhythm to effectively decouple or run slower relative to them.
And gravity itself, not just a force-bending space-time.
In this view, gravity is seen as something more active. It's a fundamental convergence of structured motion towards areas of higher rhythm density. Things are trying to sync up, essentially. It's a process of synchronization, not just passively falling down a space-time well.
Okay, synchronizing.
And even the delay of light as it travels across the cosmos can be reinterpreted. Not just distance, but a staggered process of local resolution as light interacts with these varying rhythm densities along its path.
What about the really big, perplexing cosmic questions, like dark energy, the expansion of the universe? Does motion theory offer a different take there too, not just things flying apart?
It does. Instead of a literal expansion driven by some mysterious dark energy force pushing things apart, motion theory proposes that the increasing redshift we see with distance is actually a result of phase misalignment over these vast cosmic scales.
Phase misalignment, like radio waves getting out of sync.
Kind of like that, yeah.
Yeah.
The further away we look, the more out of sync our local rhythmic patterns, our R value here, become with the rhythmic patterns of those extremely distant structures.
So the expansion is more like an observational effect of desynchronization.
That's the idea. It's not primarily about objects moving away through space, but more about this growing mismatch in synchronization across the observable universe. And this perspective even suggests there might not be a literal edge to the universe in the way we sometimes imagine it.
No, Ed.
But rather a gradual phase decoherence, a point beyond which our local rhythm becomes so completely out of sync with the rhythms of those incredibly distant structures that we simply can't resolve them anymore. They fade out of coherence with us.
That's a radically different picture. Now, this all sounds very theoretical, obviously.
It is a theoretical framework, yes.
But the source does mention that motion theory makes testable predictions, things that go beyond what standard relativity predicts. Can you give an example?
Yeah, and that's crucial for any scientific theory, right? Making testable predictions.
Absolutely.
So one area is looking for subtle shifts in clock rates under very specific, perhaps extreme conditions.
It's like where?
For instance, motion theory predicts that if you place highly precise atomic clocks at extreme altitudes, maybe much higher than satellites, or within very, very strong magnetic fields, you might induce tiny microshifts in their ticking rates that are not solely accounted for by known relativistic effects, gravity and velocity.
Well, why would that happen?
The idea is that these extreme environments could cause a slight rhythmic reconfiguration of the atoms themselves, changing their internal sync loops in a way motion theory could predict.
Interesting. Any others?
Another exciting possibility is deliberately engineering specific motion loops. Think about placing atomic clocks inside high-speed centrifuges, or maybe within rotating superconductors, where motion is highly structured and constrained.
Okay.
Motion theory predicts you could see specific, predictable rhythm offsets in those clocks due to this localized sync engineering. It would be a way to directly manipulate and measure these local time effects, offering unique tests of the theory's core principles.
That would be pretty compelling evidence if observed. It even touches on something we see in nature, how different animals seem to experience time. That classic example of the fly dodging your swat.
Right, the fly that seems to have impossible reflexes.
It's not just reacting faster, is it? There's more to it in this view.
Not exactly just faster reaction time in the conventional sense. According to motion theory, an organism like a fly, its nervous system operates with a much higher neural resolution rate than ours.
Higher resolution rate.
Yeah, its internal clock for processing sensory input is essentially ticking much, much faster. This allows it to process temporal information changes over time at a far greater speed than we can.
So time feels different to the fly.
Effectively, yes.
Yeah.
It experiences time in a more compressed way. What seems like a lightning-fast swat to us is perceived by the fly as happening in relative slow motion because its faster sync speed, its higher structured motion processing bandwidth, gives it more frames per second of reality to work with.
More frames per second, that's a good way to put it. So, okay, pulling this all together, with all these local time zones, nested hierarchies, different rhythms everywhere, and no universal clock ticking away, does motion theory basically say there's no such thing as a single universal now? That seems like a really radical idea.
It is radical, but yes, that's a core tenet. The theory firmly posits there is no master time zone.
Wow.
No universal now that everything and everyone is synchronized to. The only definition of time that's truly meaningful in this framework is local motion resolution, the intrinsic rhythm of any given system based on its structure and interactions.
And that must have huge implications for, well, everything. Causality, memory.
Absolutely. How we understand concepts like cause and effect, delay, memory storage and recall, even prediction. They all become relative to the specific rhythmic framework, the R value of the structure you're observing or interacting with. What constitutes a simultaneous room becomes highly localized.
So to really bring it all home then, what's the big insight here? We're not just passive observers watching a universal clock tick.
I think the central idea, the big shift, is that time isn't some fixed external thing out there.
Right.
It's a fundamental property that emerges from the local resolution of structured motion everywhere.
Okay.
And this leads to a universe that isn't governed by one single temporal river, but by this vast, incredibly intricate symphony of time zones, you could say. Each system, each structure operating at its own unique rhythm.
Symphony of time zones, I like that.
And crucially, we aren't traveling through some pre-existing dimension called time. We are constantly actively navigating the synchronization or the lack of it between all these different rhythmic zones.
Navigating sync, not traveling through time. That's a profound shift in perspective. It really makes you think. If our whole understanding of reality is so fundamentally tied to our own local rhythm, our own biological R value, what other possibilities, what other realities might exist out there in these vastly different time zones? It challenges how we think about the universe, for sure, but maybe even our own existence within it.
It definitely opens up a lot to ponder.
Thanks for taking that deep dive with us today. Lots to mull over there.